So, up until now, in the last few lectures, we have been concentrating on various topologies of a single transistor circuit with the aim of designing various control sources. And we saw that our humble common source amplifier was a voltage control current source, right? So, voltage control current source. An example of voltage control current source was a common source amplifier, right? So let me write it out fully. Right. Then we saw a voltage controlled voltage source with a gain of 1, right, approximate gain of 1, which was common drain amplifier. Then we saw current controlled current source, which had common gate amplifier, right? What were the characteristics? Characteristics were the primary characteristics were in terms of the R in and R out. R in and R out for a voltage control current source, R in should be high, R out should be low, right? High with respect to what? High with respect to R in should be high with respect to the source resistance, and R out should be low with respect to the load resistance, right? So if I have to write it appropriately, I should say R in should be much greater than Rs, and R out should be much less than, or rather in this case it's a current source, right? R out should be much greater than RL, and a common source amplifier was satisfying that. What about a voltage control voltage source? In case of a voltage control voltage source, what was the requirement? The requirement was R in should be much greater than Rs, and however, since it's a voltage source, which means its output resistance should be ideally 0, but 0 is not possible, so it should be much lesser than RL. In case of a current controlled current source, we wanted the current input to go in without getting divided, which means the input resistance should have been much lesser than Rs, and it's a current source at the output side, so output resistance should be much greater than RL, right? So what other voltage sources, what other control sources remain? Clearly you see that one is absent from this, and that is a current controlled voltage source. What is the R in and R out requirement for that? It's a current control source, which means R in should be much lesser than Rs, right? Ideally should be 0. What is R out? R out should be much lesser than RL, or ideally should be 0. But what is the topology? As it turns out, if you just simply take a transistor, and let's quickly run through why we could do the other three topologies by simply connecting the sources and the loads at certain terminals. We were able to do because the transistor has 2 high impedance nodes and 1 low impedance node, right? So a transistor biased in saturation has drain impedance to be infinity, right? At least that's what our model is predicting. Gate impedance is obviously infinity. However, the source impedance looking in is 1 over Gm, right? So the source is the low impedance and other two are the high impedance. Now when we wanted VCCS or VCVS, we could as well connect. In case of VCCS, we wanted two nodes of a transistor which were high impedances, and that is available. In case of a VCVS, we wanted 1 node high impedance, input node high impedance, output node to be low impedance. That was also possible because input node was the gate, output node was the source. In case of current controlled voltage source, we wanted the input node to be low impedance, output node to be high impedance. That is also possible because input node was source and output node was drain. But now we want now you want a now you want two nodes which are of low impedance, right? That is the requirement of a current controlled voltage source, and clearly we do a transistor in itself doesn't provide you two low impedance nodes. So which means we have to change course, and we'll have to think about this problem in a slightly different way. So that's what we will do in the rest of this lecture. So let's see. So before we proceed into getting into how to design a current controlled voltage source, let me take a slight amount of detour and talk about negative feedback. So what is negative feedback? What do we understand by negative feedback? So in a very layman terms, a negative feedback is a phenomena by which we observe certain output and take a corrective action based on what the output actually is and what the output actually should be. Right? Take for example, you are riding a bicycle. When you are riding a bicycle, you know that you have a path that you are traveling, right? So let's say you need to take a turn. Let's say you need to take a turn in the road, and the control knob is your handle, right? So when you are taking a turn, you know the direction in which you want to go. But when you are driving the bicycle might or might not go in the direction that you want. So in your mind, what are you doing? You are trying to figure out if there is a difference between the direction in which you want to go and the direction in which you are actually going. If there is a difference, then you are taking corrective action by turning the handle, right? You are taking a corrective action by turning the handle, and in your mind you are trying to figure out whether the difference between the actual wherever you want to go and where you are going, the difference between those two are getting minimized or not. Right? So in a very layman terms, negative feedback means observe the output, whatever the output might be, and take corrective action based on whether the output is deviating from the expected output, right? So there are three things here. One, you need to observe the actual output. Right? You need to observe the actual output. Also, you need an expected output, because you need to know where you are going. If you don't know where you are going, then there is no point in taking any action. So you need to know where you are going. You need to observe where you are actually going, and then based on that difference, you need to take a corrective action. Correct? So if we have to tabulate these, if we have to tabulate this action, or if you have to itemize this action, what we are essentially saying, we are saying that find the difference between the actual output and the expected output right. So that is number one. Number two is use the difference information to drive the system in a direction that minimizes the difference or reduces the difference, right? Instead of minimizes, let me say reduces. Right? So that is in essence how any negative feedback system works. Now depending on whether it's an electrical system or a mechanical system or electromechanical system or even a biological system, you'll have to put the system together in order to achieve this action, right? So let me show you with an example. Hopefully I'll be able to convince you. So let's say we want to design a current control voltage source, right? So in a current control voltage source, what is the expected output? Firstly, what is the input? Your input in a current control voltage source, my input is I in, a current source, right? Input is a current source, I in. Let me write input is a current source. In this case, let me say it's an incremental current source because all these things are in incremental domain. CVS input is incremental current source I in, and output is expected output, right? This is expected output is I in times output is a voltage, right? I in times some constant, and that constant, let's say, is R, right? So it's a voltage source at the output. Input is current, output is voltage, which means there has to be a change of there is a change in unit, right? So the proportionally constant, if you have to go from current to voltage, is a resistance. So let's say this is a resistance of value I in times R, right? So we need to figure this out, right? Expected output is, this is supposed to be V out, VO expected. Okay, so how should we arrange this? So let's say we have a voltage source, let's say we have a output V0. We want to ensure that this V0 effectively becomes equal to I in times R, and you have an I in, right? Let's say you have an I in, you have a current source I in. Okay, so this is the expected output. What is the real output? Real output, it is obviously the output node that you are observing, right? So this is the V out is the actual output. So you have to find a difference between the real output and the expected output. So how do you find a difference? In other words, so how do you find a difference? We need to find a difference. So difference voltage is what? Difference voltage is equal to V0 minus V0 expected, right? Which is V0 minus I in times R. Let me call this V error. Instead of writing difference voltage all the time, let's call it something. I call it error, V error. Why am I calling it V error? I'm calling it V error because ultimately, what is the goal? The goal is to make V0 is equal to I in times R. If we achieve the goal successfully, then what will be this error voltage? The error voltage will go to 0. And if it doesn't go to 0, what is it implying? It is essentially implying that we haven't been able to successfully make a current controlled voltage source which is supposed to give a output of I in times R. That's all it's saying, right? Hence the nomenclature error. So ideally we should arrange our circuit in such a way that the error voltage goes to 0. Okay, fine. So first, which means that we need to so let me also write it down. Arrange a circuit such that VE tends to 0. Okay, so then, I mean, if we have to arrange something to make VE tends to 0, then obviously we'll have to ensure that we first generate VE. So how do you generate VE? If you have V0, you have I in, you want VE. VE is V0 minus I in times R. It's pretty simple. What you do, you drag out a current of I in from V0 through a resistance R, right? So if I simply do this, what will be this voltage? This voltage will be V0 minus I in times R, which is VE. Okay. Okay. So what do we need to do? Again, let me remind you of the fact that a current controlled voltage source, or rather, when we have this I in, right? When we have this I in might have an RS. If we have a proper current controlled voltage source, this relation should hold even if you have an RS. That's the whole purpose of putting a current controlled voltage source, right? If we just simply push I in into R, I will always get an output voltage which is equal to I in times R. But that's not the goal, because if we do that, then then the output voltage is susceptible to the source resistance RS, and precisely we don't want that. That is why the input resistance has to be much less than RS, right? So anyhow, so we'll come back to this discussion point in shortly, but for the time being, let's try to design a circuit in which we can arrange a circuit in such a way that once we have a VE, we need to drive the output in such a way that VE tends to 0. Okay, so what should we do? Let's think about it. So let's assume that VE is not 0, right? Let's say VE is positive, right? If VE is positive, or let me say if VE is increasing, right? If VE is increasing, what is it telling us? If VE is increasing, what is it telling us? It is essentially telling us that the current that I am drawing out, right? The current that I am drawing out from V0 is not sufficient, right? That's what I am being told. If VE is increasing, which means the current that I am drawing out of V0 is not sufficient. I have to increase the current that I am drawing out of V0, right? If I increase the current that I am drawing out of V0, then it's likely that I'll be reducing the voltage at V0, right? If I pull current out of a node, the node voltage reduces. Okay, so now one might say that I already have a current source I in, so should I increase I in? I cannot do that because I in is not in our control, right? I in is a source that has been given to you it's an independent source. You cannot go and control it. So what we need here, we need a dependent source, because we should be taking a corrective action based on the information of VE. Note, if VE is increasing, then draw current out of V0, right? If VE is increasing, draw current out of V0, right? Similarly, if VE is decreasing, what should we do? We should push current into V0, right? So let's stick to the VE is increasing case. So if VE is increasing, we need to draw current out of V0. So what is the action that I'm interested in? Input to whatever stuff that I put here. I have to put something here so that if VE increases, I draw current out, right? If VE increases, I draw current out of V naught. Correct? So essentially we want an incremental voltage controlled current source, right? We need an incremental voltage controlled current source, right? So let's put that. Let's put an arbitrary voltage controlled current source, then we'll see whether it's realizable or not, right? So let's see, let's say we put a voltage controlled current source, right? And let's say this voltage controlled current source has a proportionally constant, let's say some G, right? Some G times VE. So if VE is increasing in the way I have drawn, I am drawing current out of this node. What is the requirement? If V increases, I should draw current out of V naught. So what should I do? I can simply connect these two terminals. Right? Let me draw it in a next page in a cleaner manner. So what I am essentially saying is this. So this is I in. So this is G times VE. This is VE, and I need to connect V naught to the top terminal of the voltage control current source, right? Okay. So this seems to be the logic, right? So let's run through the logic once again. What is this telling you? This is telling us that if VE increases, I am pulling current out of V naught, and if VE decreases, I am pushing current into V naught, right? This is all incremental, so I should actually use a small notation, right? So that was a mistake. Let me use a small notation here. G times VE. Okay. Okay. So let's see if this satisfies our case of. Firstly, what is the thing that we need to see? We need to see whether what is the input and output relation. That is the first thing. What is the second thing we need to see? We need to check whether we are able to satisfy the input output resistance criteria as well, right? So what is V naught? So let's write KCL. Let's write KCL at which node would you like to write KCL at? So let's write KCL at VE. So what is I in? What is the direction of I in? I in is this. This is I in. Where is I in flowing out from? There is only one loop, so I in is flowing this loop. So what is G times VE? So G times VE is equal to I in, which means VE is equal to I in over G, right? Right? So KCL at VE, what does it give? What do we get? We get I in is equal to V naught minus VE over R, right? Which means V naught will be equal to I in times R plus VE, which means this is equal to I in times R plus 1 over G. So this becomes V naught. What did we want? We wanted V naught to be equal to I in times R, but we have a extra factor. So but note that this G is in our control because we have put it, right? It's not. It doesn't come with the source or the load information, right? So if G is much greater than R, if G is much greater than or rather let me write in this way, if 1 over G is much less than R, i.e. G is much greater than 1 over R, then V naught seems to be equal to I in times R. This is approximately equal to I in times R. Then it looks like this can mimic our voltage control current source. But hold on, we haven't yet established whether the input output resistance criteria are satisfied, right? So let's do that next. R, this is I in, this is R, this is I in, this is G times VE, where this is VE, right? So this is my V naught. So let's say I put the I in here so that I can understand where the ports are, right? Let me use a different color for the input. I in. So this is the port, input port, and this is the output port. And this is the R. Correct? Okay. So what is the input impedance? What do we need to do in order to find out input impedance? So for R in, to find impedance, firstly we have to desensitize all the sources, right? If you have to de-energize I in, which means you set I in to be 0. If I in is 0, then the current source goes off. Current source going off means it's an open circuit. So this is what your network is. Now you have to find out the input and the output impedance. What do you think is the input impedance? What is R in? How will you find R in? For R in, again you do the same old. We apply a test voltage. Right, you apply a test voltage and then you go around and find out what the test current is. What is the test current in this case? You have a single loop. In this case, VE becomes equal to V test. Right? For R in, VE is equal to V test, which means this current, right? Which means I test, whatever is the I test, will be equal to G times V test, which means R in will be equal to 1 over G. Okay. So if the current source has a resistance Rs, right? If I in has a resistance Rs, that is, if I in comes with a resistance Rs for a current control source, we need to ensure 1 by G is much less than Rs. Right? Again, note that this is in our control, because this contraption is something that we have put in. So what about the output impedance? What will you do to find out the output impedance? Same old. So again, the source does not play a part because I in goes to 0. This is what we are left with. This is VE, G times VE. We apply a test voltage at the output terminal. We find out what is I test, right? So clearly no current flows here because other side is ground open. So this terminal becomes V test, which means G times VE becomes I test. I mean, this is the entire I test. So it essentially means I test is equal to G times V test, which means R out also is equal to 1 over G, which essentially means that if we have an RL while driving a load RL, ensure 1 over G is much lesser than RL for voltage source. Correct? So what does our final incremental model look like in the presence of sources and loads? This is what it looks like. So let me draw the contraption first. So this is VE, this is G times VE, this is R, these two go out, this is the input, I in with a source resistance RS, and this is RL, right? So this will behave like a voltage control, this will behave like a current controlled voltage source, right? If we honor two conditions, one is in this particular case, in this particular contraption, what do we need to honor? We need to honor R in should be much less than RS and R out should be much less than RL. Now note that if we do the full blown analysis in the presence of both RS and RL, the conditions that we will get will not be exactly equal to this, right? So these conditions of R out and R in that I have derived is under the condition that only either RS or RL is present. So if you do the calculations in this case, in the presence of RS and RL, you will get a slightly different result, but nevertheless it is still in your control to ensure that this circuit can behave like a current controlled voltage source. So now now you should readily recognize what is this contraption. What is this contraption? G times VE. This clearly is a MOSFET, right? What is that G? That GM is the transconductance of the MOSFET. So now let's replace the incremental model with its full blown equivalent. So this becomes again, this is I in, this is RS, right? And we have RL, and instead of G times VE, we have to put a MOSFET where this is source is grounded, right? Source is grounded. We have a resistance between the drain, right? So this, okay, let me mark the terminals here. This should be the drain, this should be the source, this should be the gate, correct? So we have a resistance between drain and the gate, correct? So we have a resistance between the drain and the gate, and then we'll have to ensure that the inputs are also connected, right? So how do you want to connect the input? We would like to connect the input the same way as we have been doing. We'd like to connect the input through a AC coupling capacitor. So let's say we put a coupling capacitor here, right? Let's say C1, let's say coupling capacitor here, let's say C2, right? This is R. But you might be now screaming at me saying that how have I biased the transistor M1? This is clearly not biased, because what is its get to source voltage? What is the current flowing through it? Clearly nothing, right? The get to source voltage is not applied, it's zero in this case, right? So what should I do? I can simply put a current source, right? We can put a current source bias. Where do we want to put? In this case, it seems like since I already have a connection between the drain and the gate, right? The connection between drain and the gate is already established. The easiest thing to do will probably be to mimic that condition in which we observe the drain and feedback at the gate, right? So this can be the IDC bias. Okay, so this will be V naught. Okay, so what I would request you to do, this essentially becomes my full blown current control voltage source with biasing in picture. What I would request you to do is find the constraints on the sizes of C1 and C2, and also the swing limits of I in. If I in is equal to IP sine omega naught. Okay. So this will be your assignment for the week. This will be one of the assignments for the week. It might be instructive to go through it on your own, right? Okay, I'll see you in the next class.